we defined the transfer operator. So this is the operator T hat acting on L1, which describes the action of a dynamical system on the mass densities. So the idea is that if this is the space X and you distribute mass in some non-even way, the mass distribution is described by some density F. And if you apply the transformation T, then what will happen? Different parts of the space will move to different places. Very likely they will move in a very chaotic way if the map is chaotic. And then what the transfer operator tells you is what will happen to the density of the mass. And the basic principle in this business is that the more chaotic the system, the better is the behavior of the transfer operator. Chaos is helping you when you're acting on mass densities because it regularizes the behavior. It's kind of like you have a tray of sand, you shake it, and the sand immediately evens out. Now, because of this phenomenon, what we expect is, we expect for chaotic maps T that when you apply the transfer operator many times to a density, then it will converge very fast to some limit. The limit, as we discussed last time, is going to be an absolutely continuous invariant density for the transformation. Now, what I would like to do today is to start discussing tools for proving that something like this happens. So today we will discuss tools for showing this. Now, what is nice about the transfer operator approach is that the transfer operator is a linear operator. It's a linear operator on L1, and this allows us to bring into the game tools of functional analysis and measure theory. And we are going to make very heavy use of such tools. More precisely, we are going to discuss two properties which are meaningful for general operators acting on general Banach spaces, and they are called quasi-compactness and spectral gap. Okay, so before I tell you what quasi-compactness and spectral gap are, I'd like to give you a brief review of some definitions from functional analysis. I'm sure that almost all of you know this stuff, but I want to fix the terminology because maybe, I don't know, it's worth doing. So here's a brief review. So suppose L is a bounded linear operator on a Banach space B. In our case, L is going to be the transfer operator, T hat, and the Banach space, well, we're going to talk about it later, but it's going to be some subspace of L1. Formula for the transfer operator, sure. I will not write the formula for the transfer operator because it's not very useful, but I will write the property which characterizes the transfer operator, which we discussed last time. So T hat F is determined by, for every test function in L infinity, the integral of phi against T hat F is the integral of phi composed with T times d mu. Okay, so this determines the action of the transfer operator on L1. Yes, this is in special cases. Yeah, in special cases, yes. But this definition makes sense for general non-singular maps. Okay, so suppose that L is a bounded linear operator on a Banach space, then the eigenvalues, well, this is just like in ordinary linear algebra. These are numbers lambda. I will always work on the field of complex numbers for reasons that will become clear tomorrow. So these are numbers lambda such that LF is equal to lambda F for some F non-zero in the Banach space. The multiplicity is the dimension of the collection of vectors which satisfy this. In particular, if the multiplicity is equal to 1, we will say that the eigenvalue is simple. So simple means multiplicity 1. Okay? Now, the reason I'm mentioning eigenvalues is because I want to contrast it with the notion of spectrum, which is different in infinite dimension. The spectrum is defined to be the space of all lambdas for which the operator lambda I is the identity minus L, has no bounded inverse. Now, if you think about the definition of an eigenvalue, if lambda is an eigenvalue, it means that this operator has a kernel, so it's not one-to-one, so it has no bounded inverse. And in finite dimension, that's the only way that this operator can fail to have a bounded inverse. But in infinite dimension, and we will always work in infinite dimension, there can be other reasons for this operator not to be invertible. For example, it's not necessarily onto, even if it's one-to-one. Okay? So the spectrum contains the eigenvalues, but in general, it may contain many other points. And there are even examples of maps which have no eigenvalues and huge spectrum. Okay? So what I would like you to remember is two things about the spectrum. The first thing that I would like you to remember is that in general, for infinite dimensional spaces, the spectrum could be larger. Well, it's not always larger, but it could be larger. Okay, that's what I mean. And the second thing that I would like you to remember when we're talking about spectrum is another phenomenon that is infinite dimensional in nature, and that is that the spectrum depends not only on the operator, it depends on the Banach space. The problems which prevent an operator from being invertible are not only a function of the equation which are defined by this, they're also a property of the space of possible solutions. So the spectrum depends on the space. Depends on the space. The reason I'm saying this is that when we define the transfer operator, we define it on L1. However, as you will see today, it's very useful to consider the action of the transfer operator on other spaces, which are much smaller than L1. And the reason is that by playing with the space, by changing the space, we can change the spectrum. And this will be the game that we're going to play. Now, it is a fact that the spectrum is a compact subset of, the complex numbers. And it has a diameter. And not a diameter. It has there is the radius of the largest disk centered at the origin, which contains it. That's called the spectral radius. So the spectral radius is rho of L. It's the limit. It's known that the limit exists of these numbers, and this is also equal to the infimum of these quantities. So this is the sup, or even the max, of Z in C. Sorry. It's the maximum of the absolute value of Z, where Z is in the spectrum. Okay? This is the spectral radius. And now I finally come to the, question. I'm sorry? In the case of the transfer operator, it's 1. But it's 1 over... No, it's like this. Yes, you are right. You are right. You are right. But no, but I actually want to use it like this, and then I have to put infimum of this. I want to keep this this formula. Okay, so now I come to the definition, which is spectral gap. So we say that L has spectral gap on a Banach space B if you can write L in the form L is lambda P plus N, where P is a projection. This is the equation P squared equals P. And the dimension of the image is 1. N has spectral radius strictly less than lambda. And still have room. And P is equal to 0 and Pn equals to 0. Lambda is this number. So the statement is that there exists a representation of the operator in the form lambda times an operator P, which is a projection, P squared equals P, plus a sort of arrow, which has strictly smaller spectral radius. And now, no, we are talking about Banach spaces. We are talking about Banach spaces. Unfortunately, if in cases where you can make the transfer operator act on a Hilbert space, you are very happy, but usually this is very difficult to do. No, we are in the... Unfortunately, we have to work with Banach spaces. Now, why is this relevant to the problem of describing the iterates? This is because of the following observation. So, so notice, if you take L to the power n, what do you get? You get lambda P plus n to the power n. So this is lambda to the power n, P to the power n. Then you have mixed terms. By mixed terms, I mean terms that contain np or pn. And then you have n to the power n. Now the mixed terms are 0, because we are assuming that n and p, they kill each other. So the mixed terms are all 0. So you're left with lambda n pn plus nn. What about p to the power n? P times p is p. P times p times p is p. And so on. So p to the power n is p. So this is p. So what you get is that this is equal to lambda to the n p plus n to the n. So lambda minus n times L to the power n converges to P very fast. This is going to be lambda minus n n to the power n. Now, n to the power n is controlled by the spectral radius of n. So this is less than lambda to the minus n, and then I'll take e to the epsilon rho n, everything to the power n, for some epsilon. And this will be because we can always choose epsilon such that e to the epsilon rho n is less than lambda, this will be exponentially small for some theta between 0 and 1. In other words, if you have spectral gap, then you know that lambda minus n L to the power n converges very fast to a limit, exponentially fast. Okay, so what we are going to try to do is we are going to try to find Banach spaces such that the transfer operator has spectral gap on them. And then it will follow that the iterates of the transfer operator converge to a limit and even converge exponentially fast. Okay? So that's the spectral gap is the goal. That's what we would like to show. Now, I'm sorry? Why the name? So let me explain to you why the name. Now, I don't have time to give you complete explanation, but you will find an exercise which says precisely what I'm going to say now in the notes, and there will also be hints how to show it. So the name is because of the following thing. So why the name? So in this case, so this is an exercise, but you need hints. There are hints in the notes how to do this. In this case, the spectrum looks like this. This is the spectrum of L. The spectrum is always enclosed in this disk of this side. There will be a single eigenvalue, which is simple. And then there will be a gap. And the rest of the spectrum will be inside. So in the case when you have spectral gap, the spectrum of L looks like a simple eigenvalue plus something else, you don't know what it is, which lies in something which is separated. And the gap is what gives the spectral gap the name. This is in fact equivalent, although at this point you can only show one direction. You will be able to see the other direction after tomorrow. Okay, now, so we define spectral gap. It turns out that from the theoretical point of view, it's more convenient to handle another concept, which is slightly weaker, which is called quasi-compactness. So what is quasi-compactness? Quasi-compactness L is quasi-compact if you can decompose the space. If you can decompose the space into two pieces where F and H are closed subspaces and invariant, such that L, F is inside F and L, H is inside H. F is finite dimensional. And H, well, usually it will be infinite dimensional, but what is important about H is that the spectral radius of L restricted to H, because H is invariant, you can think about L as an operator from H to H. So the spectral radius of the part of the operator that lives on H is going to be smaller than all the eigenvalues of the operator on F. Lambda is an eigenvalue of L on F. Now, example. Well, we'll see a real example later, but for the time being, if you have spectral gap, you always have a decomposition like this. If L has spectral gap, then what you need to take is you need to take F as the image of P and H as the kernel of P. And this will be the decomposition. Now, from the spectral point of view, if this is the case called spectral gap, then this will be the case, the general case of a quasi-compact operator. It's almost the same picture, except that we allow other eigenvalues on the circle. And maybe some more eigenvalues inside, but finitely many, and something crazy without any control, bounded away. Okay? So these are going to be finitely many eigenvalues of finite multiplicity. Okay, so this is the case of quasi-compactness. In fact, the only difference is the other eigenvalues on the boundary plus the multiplicity. If you have a quasi-compact operator which has only one eigenvalue of maximal modulus, and this eigenvalue is simple, then you have spectral gap. Although again, to prove this, you will need tools that I will describe tomorrow, not today. Now, let's go back to the dynamical context. And let me tell you what happens in the dynamical context. In the dynamical context, there is a theorem which is a sufficient condition for quasi-compactness, which I'm going to explain to you in a short while, well, now, which can be used to show that the transfer operator of many dynamical systems has a spectral gap on certain Banach spaces. It's not spectral gap, it's quasi-compact on certain Banach spaces. Now the question is, how do you pass from quasi-compactness to spectral gap? Because the real difference between quasi-compactness and spectral gap is the existence of other eigenvalues on the circle. What you need to do is you need to rule out other eigenvalues on the extreme circle. And this is done by mixing. So there is a guided exercise in the notes which says the following thing. And this is the way that quasi-compactness is used in the dynamical context. I don't know why I did this. Didn't gain anything. Okay. I'll just write down the exercise. It's not difficult, but I don't have time to do it. So here's an exercise with guidance in the notes. Suppose T hat is the transfer operator of a dynamical system X B mu T, a non-singular map. T acting on a probability space or measure space X B mu, and assume there exists a Banach space B inside L1 such that the norm of B is stronger than the norm of L1. T hat preserves the space and is bounded as an operator on the space. And T is quasi-compact. T is quasi-compact on B. Okay? If T has a mixing absolutely continuous invariant density, probability density, then T hat has spectral gap. Non-zero. So non-vanishing, non-vanishing. I also need. I don't want the trivial. I don't want the trivial Banach space. I don't want zero. Then under these conditions, T hat has spectral gap with lambda equals 1, and P, the operator, is going to be Pf is H integral df mu, where H is the absolutely continuous invariant density. So the point here is that mixing, if you are in a context which is mixing, then you don't really need to prove spectral gap. It's enough to prove quasi-compactness, because mixing can be used to rule out the eigenvalues on the boundary, and you are left with spectral gap. Yes. It means that in the representation T hat equals lambda p plus n, the representation which defines spectral gap, lambda is equal to 1, and the projection operator P is the map which sends a function f to a constant times h, and the constant is this bounded linear functional. So the spectral gap, the image of the projection is one-dimensional, so everything, all the images are proportional to the same thing, and that's what it means. Okay, so now that we know that at least in the mixing context, in order to prove spectral gap, it is enough to prove quasi-compactness. Let me show you the tool that everybody uses to construct Banach spaces with on which the transfer operator acts quasi-compactly. So this theorem has a very, very long history, starting from the 30s in probability theory, going all the way to the 90s. I will give you the most modern version which I'm aware of, due to Henyon. It's a little bit long. The proof is much, much longer. You can find it in the notes. I'm not even going to pretend that I can do it in the time that I have, but you can find the proof in the notes. And here is the theorem. Actually, this theorem I will write here, because we will use it later. So a sufficient condition for quasi-compactness so theorem Henyon. Well, this is a generalization of theorems which were proved earlier by Ionescu, Tulcea, and Marinescu, and before that by Devlin and Forte in a probabilistic context. Suppose L is a bounded linear operator. B is always a Banach space. I'm always in the context of Banach spaces. And assume there's a semi-norm such that, so now comes a long list of conditions. But I will show you an example. First condition is that first of all, what is a semi-norm? A seminorm is like a norm, except that some non-zero vectors may have seminorm 0. Okay, so it satisfies all the axioms of a norm, except the one that says that if the norm of V is 0, then V is 0. There exists a seminorm which is continuous. So continuity, the continuity axiom says that F maps to the norm of F is continuous on B, of course with respect to the norm of B. The operator has to be bounded also with respect to the seminorm. There exists a constant M such that the seminorm of LF is less than or equal to a constant times the seminorm of F. And now comes an important condition, precompactness. Now the various versions of this theorem along the history vary in the way that they state precompactness. So what we would like is the following thing. If you have a sequence of elements in the Banach space whose norm is bounded, then there exists a subsequence and there exists an element of the Banach space such that L, F, and K converges to G with respect to the weak norm, with respect to the seminorm. Now, since we are in infinite dimension, balls, bounded balls, are very far from being compact. They are not compact. They are not sequentially compact. Okay, so it's not true in infinite dimension that every bounded sequence has a convergent subsequence. What we are asking is something much weaker. What we are asking is for a bounded sequence to have a convergent subsequence in a weaker norm. Not in the norm of the Banach space B, but in a weaker norm. This is possible. Okay? This is possible. So that's the point. That the compactness condition is specified not in terms of the norm of the space. No reason for that to happen in infinite dimension. It's specified in terms of a weaker norm. Okay, so if this was an important condition, now comes the real heart of the matter. So this is the most important condition. It's called the Deblin-Forte inequality. Or the Lasota-York inequality. But it appeared already in the 30s in the work of Deblin and Forte. There are numbers are smaller than the norm of L, and capital R bigger than 1, and some power and 0, such that L and not F is less than or equal to R and not F plus capital R seminorm of F. Okay. So long list of conditions, then L is quasi-compact. Okay, that's the conclusion. So under all these conditions, L is going to be quasi-compact. Now the heart of the matter is, of course, this inequality. Look at this inequality for a minute. Imagine that N0 is very, very big. You can arrange this by iterating the operator. If you iterate this, you get this inequality with bigger and bigger n's. Now the way to think about the pair of norms, the norm of B and the seminorm, is the following. The seminorm in applications measures size. It can be the L infinity norm. It can be the L1 norm. If you take a constant function that is equal to 100, it will have 100 times the norm of a constant function equal 10. Okay? So the semi-norm measures size. In applications, the norm of B measures regularity. It can be the Lipschitz norm. It can be the bounded variation norm. It can be many other norms. But the point is that if you have a function that looks like this, so a function like this, think intuitively that such a function has very small semi-norm and very big regularity norm. Now, what this inequality is telling you is that if you start with a function that has a big regularity norm, highly irregular, and you apply the operator, then the norm of the result is not going to be very affected by the fact that you started with a function with big B norm. The norm of the result is going to be really close to the size norm, which means that when you take a highly irregular function and apply the operator many, many times, it smoothens it out. Or rather, I should have said it in a different way. The mechanism which produces the Deblin-Forte inequality is the mechanism of smoothing things out. You take a function which is highly irregular, apply the operator many, many times. The norm of if the operator smooths things out, it will kill the part of the norm which is responsible for regularity. It will only leave the part of the norm which is responsible for size, total mass. And then the result will be really determined by the size. The term which fills the regularity of the function is multiplied by something which is exponentially small. Yes? This is a slight generalization of the UNESCO-Tolchiamar-Ionescu theorem. The differences are in the boundedness assumption and the precompactness assumption. Here, the precompactness, you only ask for precompactness of the image of L, rather than for you're not saying that the ball is precompact, but that the image of the ball under L is precompact. But it's really the same, it's really a sharpening of the UNESCO-Tolchiamar-Ionescu theorem, as you say. Okay. We have a little bit of time, so I'll show you how to use. Okay, fantastic question. The reason I constantly mix up the spectral radius and 1 over the spectral radius and all this stuff is that in the context of transfer operators, the spectral radius is always 1. So it will indeed be, this condition will indeed, in the case of spectral operators, say that R is less than 1. Now, in the case when R is not less than 1, then what people do is they apply this theorem not to L, but to 1 over the spectral radius times L. And then it's again less than 1. But you're absolutely correct. I'm sorry, in my mind I always think about the spectral radius is equal to 1. Okay, so let me briefly start showing you an application of this theorem. Where did I put the... Okay, we'll start today and we'll finish tomorrow. So here's an application. It's a very famous application of this type of techniques. It's an application to continued fractions. So if you have a number x, admits a unique expansion, admits a unique representation in this form. Where A, K take values in the natural numbers. And it's an observation that goes all the way back to Gauss. He mentioned it in some letter, but people don't know how he found this phenomenon. What Gauss noticed is that if you pick X randomly in the unit interval, and you plot a histogram of the values of AK, for K very large, well, some numbers will have Kth digit equal to 5, and some numbers will have Kth digit equal to 11, and so on. So you can plot a histogram. And what you notice is that if k is very, very large, then the histogram has a sort of a limiting shape. And even said what the limiting shape is. The limiting shape is, there's no color shock. Okay, so this is a histogram of the value of AK. So it tells you that the total the probability that X will have AK between n and n plus 1, it will be the area below this column. That's a histogram. And what Gauss found was that there is a limiting shape, which is the famous function 1 over log 2 over 1 plus x, ln 2. Well, log is ln. Now, nobody knows how he got this. He probably just calculated. It was Gauss. But later it was proved to be the case. First, the limit theorem was stated with rate of convergence stretch exponential. That was Kuzmin. And later, by Levy, it was shown that the approximation is exponentially good. So here is the statement. Gauss, Kuzmin, Levy, let M be the Lebesgue measure, then for every n, the measure of the set of points for which AKX equals n equals 1 over log 2 integral from 1 over n plus 1 to 1 over n dx 1 over x plus O theta n for some theta between 0 and 1 and uniformly in n as k goes to infinity. Okay? So this says that the convergence to this curve is the convergence to what is produced from the density with this curve is exponentially fast. So so how is this related to the transfer operator and to the quasi-compactness of the transfer operator? So the connection is through the Gauss map, the famous Gauss map. That's probably the reason why the Gauss map was invented. So here's a sketch of proof. So let T be the Gauss map T of x is the fractional part of x. So what's the point? Why is this a relevant notion? So notice that T of 1 over A1 plus 1 over A2 and so on, what happens? You take 1 over and then you get this. Then you take the fractional part, you get this. So the effect of the Gauss map is to remove the first digit. If you do it k times, you get the kth digit. And the result of this is that, so, the Lebesgue measure of the event that AK equals n This is the Lebesgue measure of the event that tkx belongs to, well, has a continued fraction which starts with n. So it's going to be inside the set 1 over n plus 1, 1 over n. This is the integral of the indicator of the interval 1 over n plus 1, 1 over n, t dm. And now we apply the characterizing property of the transfer operator. I can write this as this bounded function composed with t times the constant function 1. So by the definition of the transfer operator, this is t hat n 1 times the indicator of 1 over n plus 1, 1 over n. Now, you can see from this formula that if we can show that the transfer operator applied to the constant function converges exponentially fast to the only possible limit, which is the absolutely continuous invariant density, then we'll get this result. If we can show that t hat n1 converges exponentially fast in L1 to the absolutely continuous invariant density, then we are done. Because if this converges in L1 to the density, then the integral converges to the integral of the density. So the only thing that we need to do, notice the task now. The only thing that we need to do is to find the Banach space which contains the constant function 1 on which we have quasi-compactness. We only need to worry about the constant function 1, okay? So in this game, small is good. The smaller the Banach space you have, the better the results you are going to get. We only need the constant function 1. Of course, the Banach space needs to be closed under the action of the transfer operator. So we need to take 1 and the image of 1 and the image of 1 and so on. And then we need to close to get a complete space. And the question is with respect to what norm to close. So the only thing that we need to do is we need to find a norm such that if we close 1, T1 and so on, we close it with the norm, we get a Banach space with on which we have a quasi-compact action. So let me show you what is the Banach space and then we will finish. And I have to think whether to show you the proof or not. It's in the notes anyway. The proof that the Banach space satisfies the condition of Hegnion's theorem. So the Banach space is going to be f from 0, 1 to c, f is Lipschitz, with the norm L infinity norm plus the Lipschitz norm, Lipschitz constant. This is, of course, the sup fx minus fy x minus y. And you take the semi-norm, you use Hegnion's theorem with the semi-norm, which is the L1 norm. Now, what is remarkable is that the transfer operator, being an averaging operator, and now I will write you the formula of the transfer operator in the particular case of the Gauss map. We found it in the last lecture. So I remind you that the transfer operator is sum a goes from 1 to infinity, 1 over a plus x squared f 1 over a plus x. This is an averaging operation. And the fact is that this averaging operation regularizes the function. If you start with a function with big Lipschitz norm. After several iterations, not too many, the big Lipschitz norm will disappear, and what will remain is the size. Okay, so we're out of time. Either next time I will show you that this space satisfies the condition of the Nyon theorem, or we will move to another topic. Anyway, the complete details are in the notes. So thank you.